So we're going to start on pages 4 and 5. What were your struggles for that? No struggles? You were cool? It's not what I heard. So well, I'll talk about the struggles that I saw along the way. So as long as we're at it, I already heard a few of you talking about what's up there in the orange on the board. So we're going to have a quiz on Tuesday. It turns out that's the 12th. Had to look up the date, did not know. Tuesday, December 12th. It's going to be solely on ESRT pages 5 and 10. So 5 is the one with the plate tectonic map. So talking about convergent, divergent, transform, all those good things. And then page 10, which is this reference table we're using today. It'll be about 10 questions, so it won't take the whole period. We'll keep going after that. So keep in mind, though, that if you had any questions on what we were just working on, make sure you get those cleared up by the end of today. So let's start with the depth range. I think those first two depths, especially the crust, was kind of on the tricky side. So remember, depths are listed on the x-axis down here. So where is the crust on this graph? All the way to the left. When you say all the way to the left, please notice. So I colored the entire lithosphere here brown. I'm not sure what color you used on your own. But keep in mind, of that little tiny layer, the crust is just this black line. The crust does not even include what used to be a white line, but we colored it. So the crust doesn't even include that. So if we followed where that black line would be, that comes up, for me, I set it 0. The crust goes from, I said 0 to around 50 kilometers. You can't even see 50 on this graph though. So if you said 0 to 0, that would be the crust. But the crust does not extend beyond around 50 to 60 kilometers below the Earth's surface. So that one was sketchy on the graph. And I will let you know that I don't think the Regents would ever ask you about the depth of the crust because it's too hard to read on this reference table. I do think the asthenosphere was fair game for the depth. So that's my green layer. And you can see that the green layer starts really close to the 0, but off a little bit. So if you said it starts at around 50 or 100, I'd say that was good. And what do you guys estimate it ending at? So the end of my green layer here. Yeah, I'm glad nobody said 500 because this is more than halfway across from the 0 to the 1000. So I did say 50 to 700, but if you said like 100 to something around 700, you're good, as long as it wasn't up to 1,000 or below 500. Then the stiffer mantle, this is where it got a little bit easier. I said around 700 to 2,900. Please note that this pink layer for me does not make it all the way over to 1,000 or to 3,000. So cut that off before 3,000. I said 2,900. But somewhere around there, just not 3,000. All right, outer core, I said 2,900 to 5,100. Again, that does extend beyond the 5,000. So make sure you had that bigger than 5,000. And then again, 5,100 to around 6,200 or 6,300. All right, how far is it down to the center of the Earth? Again, I had to estimate that. I said 6,200 or 6,300. Again, please note it is not a full half a box. This is not big enough to make it to 6,500. And then the mantle outer core boundary. Again, they didn't ask about the mantle. They didn't ask about the outer core. They want the boundary between them. So you follow that down. That's the one that's around 2,900. Now the thickness, I saw a bunch of you leave that blank and I ended up giving you full credit even if you left the thickness blank because sometimes we need just a little extra reminder how to do that. So if we know where a layer starts and where a layer stops, the thickness is just, well, how big is this area? And to figure that out, if we know where it stops, we know where it starts, and you subtract those two numbers, that's how thick it is. So all I did was I took my 50 minus 0 and got 50 for the crust. My 700 minus 50, and that's where I got 650 for the asthenosphere. Your numbers might be different if these numbers were different. 6,200 for the stiffer mantle. No, 2,200 for the stiffer mantle, which is exactly the same as the outer core. And then the inner core, 1,100. So again, your numbers can be different than mine if your numbers up here were different too. Density, hopefully you had no problem with that. Just literally copying it off of the chart right here. So they do separate the two different kinds of crust. I didn't mention this yet. 2.7 for granitic continental crust and 3.0 for basaltic oceanic crust. What do you think they're trying to tell you there with those words granitic and basaltic? What it's made out of. So what's the ocean crust made out of? Basalt. Now it says basaltic. That's just saying it's made out of basalt. And I'm assuming you can figure out granitic, made out of granite. Okay, so basalt and granite have slightly different densities. Keep that in the back of your head, that granite and basalt have slightly different densities. Then going from the rest of the list, remember, we talked about this the other day, that brown layer is still stuck in the mantle section. So it's going to have 3.4 to 5.6. Same with the asthenosphere and the stiffer mantle. So asthenosphere 3.4 to 5.6, stiffer mantle 3.4 to 5.6. Outer core 9.9 to 12.2, inner core 12.8 to 13.1. And as long as you've got a up graph there, I did see some people be a little more specific and kind of curve it like that. That's good too, as long as you realize it's a direct relationship. When depth goes up, density goes up. Now, pressure, I did not ask for a range for pressure. I just asked for the highest pressure. So again, the crust, that black line, the crust is at 0 depth, basically. And as you can see from the reference table, it's at 0. So the highest pressure for the crust, put temperature here because I wasn't reading carefully once again because I was in a hurry. So that's going to, there's my pen. Nope, that's not it. That's going to be right at 0. What'd you say for the asthenosphere? The highest pressure. So this green layer is my asthenosphere. So there's the lowest, there's the highest for the asthenosphere. What'd you estimate that to be? Okay, I heard some 0.1s or 0.2s. Really close to 0 is what you should be noticing there. The stiffer mantle, what'd you say there? I also was thinking 1.5. And the outer core. Yeah, around 3.1-ish. And inner core, 3.5 or 3.6. That one, it is hard to tell exactly where it is. Now, this was not multiple choice. I always have people just circling a random answer there. This was asking at what depth are these pressures found? So 1 million atmospheres, that's right there. I want to know what depth that is. So you go to here and you read down, and I said it was about 2,900. But I think that was wrong. Yeah. Yeah, I'm not sure where I got that from now that I did it. So 1 million atmospheres hits right here. Travel down with that. It's definitely closer to 2,000. I'd say like 2,400. Not actually sure where the heck I got that number from. 2,400. Hopefully I did the other ones right. 2. Yeah, okay, that one I think is 3,500. Do you guys agree? You got that too? Okay, how about 5,000? Okay, so I don't know what I did with number 1. And then again, hopefully you notice that as depth increases, pressure increases. How hot can the following sections get? Again, I can't read the crust. I'm not exactly sure where this line is. So I said anywhere between 500 and 1,000 for the crust. 2,500 for the asthenosphere. 5,000 for the stiffer mantle, 6,200 for the outer core, 6,600 for the inner core. You guys good with those numbers too? Comfortable using this reference table? All right, good. What depths are these temperatures? So again, I think it gets sketchy over here at the very beginning. 1,000, it's hard to say exactly where that hits. I'm saying like maybe around 100 or 200 kilometers. Then about 400 for the 2,000 and about 900 for the 3,000. 1,800 for 4,000, 3,000 for 5,000, and 4,500 for 6,000. Which layer did you guys think had the greatest rate of change, where it increased temperature the fastest? Okay, you're saying the stiffer mantle. Why'd you say the stiffer mantle? It went up the most, but does that mean it increased its rate the fastest? No. We want to know how did you look then? How steep the slope was. That's what we're looking for, is the place that has the steepest slope. I'm not going to deny this did increase the most, but it was a slow, steady rise because the mantle's so thick. Over in this section, and to be honest, I can't tell if it's the lithosphere or the asthenosphere, so I would have put down either one of those as your answer. The outer core is the layer that's melted completely because the temperature is greater than the melting point. And the asthenosphere is that ooey gooey layer. Ooey gooey, partial melting, I guess is what they call it. But ooey gooey sounds so much better. There anything on page 10 that is a little unclear or anything with you guys? All right, let's hear what you had to say about yesterday's stuff then. So as I mentioned yesterday, I was kind of asked you to, I asked you to do this in pencil just in case there was anything that needed to be changed. These are your notes for this section. This is the only time we're going to be talking about continental drift and how Alfred Wegener knew about continental drift. I did realize though that I forgot to share one very important part of continental drift yesterday. You may have heard about it later on in the day, but I'll bring it up now. Give me 1 second. Continental drift. Somebody asked me yesterday during lab what my favorite song was, and I couldn't.
A verbo is for sharing all kinds of moments.
Them at the moment because it was going to ruin
From teeing
my
off,
surprise. Here's my
spilling
favorite
tea.
song of all time. Oh, why are we not?
In the year of 1910, there was a scientist whose name was Alfred Wegener. He noticed that the continents looked just like pieces of a broken puzzle. By 1915, he called it continental drift. It caused a rift with his fellow scientists who sang, ha ha, Alfred Wegener, you are a crazy man. Ha ha, Alfred Wegener, you are a crazy little man. science could do this. And until you show just how or why, you merely have one interesting hypothesis. Until this evidence we see, you don't have a theory. Ha ha, Alfred Wegener, you are a crazy man. Ha ha, Alfred Wegener, you are a crazy little man. In the year of 1930, on an expedition to Greenland, Wegener got caught in a blizzard. When they finally found him, it was much too late, and they buried him in an icy mausoleum. 30 years after he died, a new idea came to light. It changed the way geologists saw the world and brought continental drift back to life. Now everybody sings, yeehaw! Alfred Wegener, you are a brilliant man. Yeehaw! Alfred Wegener, you are a brilliant, brilliant man. Continental drift, Alfred Wegener's theory, continental drift. Alfred Wegener's theory, continental drift. Alfred Wegener's theory, continental drift. Alfred Wegener's brilliant theory.
Legit, my favorite song ever. No, you're so full of it. It's very catchy. It does have a good beat. If you guys have already found my TikTok, I'm sure you've already realized that I definitely danced to that during COVID. Don't you? Oh, and you're questioning me for having one and you're a teenager without one. Okay. I don't have Twitter either. I don't understand Twitter. Yeah. What? So I don't know Sid the Sloth. I think, didn't we talk about this yesterday? I am probably, yeah, I hear I'm a horrible science teacher for not, and a horrible parent because I don't know Sid the Sloth and Continental Drift, the movie. I say once a year, I'm like, it's always right around Christmas when we're doing this unit. I'm like, okay, I'll watch it over Christmas break, and I never do. Probably the worst teacher ever, but moving on. Love the song. It told a good story about Alfred Wegener. By the way, Alfred Wegener is the person who came up with this theory. We talked about it a little bit yesterday, but he came up with it in 1910. What we didn't talk about yesterday was how they literally said he was nuts. They're like, okay, you've got some evidence. You guys talked about the evidence yesterday, but he didn't have an explanation for how or why this could happen. And so like the song said, well, he had a great hypothesis, like an educated guess, but he had no way to prove it. So it was just a hypothesis, no theory there. So it was kind of useless to the scientific community. And the poor guy literally died during a blizzard. And never, his ideas he thought they died with it. But then after World War II, after they were mapping the sea floor, checking for submarines and underwater like bombs and stuff. So that's why they were mapping the floor in the first place. And they realized, holy cow, there's some evidence to support the how and why for Alfred's theory from forever ago. And so 30 years after this poor guy died, his idea became one of the most famous geology theories there are. And he never knew it. Yesterday, I asked you to go through these different slides and pull out the most important information. We already did yesterday, the shapes match. Basically, the key idea of that slide was that it was like a giant puzzle piece. Like you can put together the continents like are shown here. The next slide was that plants and animals matched. Now this one might have been a little confusing, but what was the gist that you were getting out of this one? What notes did you put in your packet for this one? Say that again. There, that's the part I was only hearing the different part. I needed the same part. So that might not like be evidence to you guys yet. But if we pull in some of the stuff you learned last year, can you guys think back to the Bird Beat Lab talking about the different finches on the different islands in the Galapagos? Okay, so you're gonna have to try and pull that memory out of your brain cells for a few minutes. So what I did here is I brought up a picture of the Galapagos. They're these teeny little tiny islands off the coast of South America. Teeny tiny. We're not talking about sizes of continents. We're talking about even little teeny tiny islands. I blew them up over here so you can kind of get an idea. Do you guys remember some of the main points of this activity or like some of the takeaways from this? There was evolution was the main idea here. And what did you learn about evolution on these different islands? Right. Each island, the birds needed to adapt to that island. So basically, like some of the earth science takeaway I get from what you did last year, or at least the basic understanding I take away is each one of these islands had their own bird, right? And a bird that lived here on this island probably couldn't live on this island. Now, one other thing, could a bird that's on this island, could they have just flown to this island? They could have. Could they have flown from here to here? We're talking about little finches. Could little finches fly across oceans? Probably not. And this, I'm not sure if they brought this part up because this did not really apply to what you were learning last year, but it's important for this year. Guys, little finches, they need to eat regularly so that they have energy to keep going. There is no way, maybe from this one to this one, maybe from here to here, but there is not an easy way for finches to get from one island to the next. They wouldn't have enough energy to fly from one island to another. So what I'm getting at is last year you learned that if places are separated even by a small amount of ocean, the birds develop differently on each island. And you wouldn't find a bird from this island on this island or this island. They all stick to their homes. So then if we think about the whole world, like, I don't have the picture of the whole world here, but South America and Africa, can you picture them right now? And if you can't, there's page 5 of your reference table you can look at. Are Africa and South America very close right now? No, right now they're super far away. And if there was a bird, or in this case, whatever this lizard creature was supposed to be, a what? It's that word, I don't know what it says. I can't, we'll go with that, sure. I don't even pretend I can pronounce dinosaur names because I can go with T-Rex and that's about it. I can spell that one. I can't spell any others. But anyway, whatever these creatures were, they were not just crossing the entire Atlantic Ocean to go and live in South America and Africa. Based on what you learned about the Galapagos Islands, you should realize that there will be slight differences. Even if there was a similar species, they would be their own version of each other. Like today, whatever was living on South America could not live exactly the same on Africa. It would have to have evolved into a slightly different organism. But what Alfred Wagner found, which is in this picture up here, I think I blew it up on the next page. What he found is, so is this what you said? Yeah. Say it again louder. Mesosaurus. Okay, I could have figured that one out. So this Mesosaurus Not only did they find this Mesosaurus, I think it's this orange, dark orange guy here. They found the Megasaurus, exactly the same Megasaurus fossils, like they hadn't adapted at all. They found fossils for them on the southern tip of South America and the southern tip of Africa. But again, thinking back to the real world today, they're really far apart. So Alfred Wagner's like, the only way that these guys could have existed on both continents is that both continents had to be next to each other. Because where Africa and South America is today, they would have evolved into two different species. Same with all of these. You want to pronounce that one? No? Okay, yeah, I got nothing for that one. I know something, I'm guessing. Same with that one. It was found on South America and Africa, the exact same species. We know that they would have had to evolve differently now. Wow, you guys know things that I have no idea about. So in that section, that plants and animals fossils matched, what was the title officially? Oh, well, okay, so all right, plants and animals match. We have to say, so something about the exact same fossils found on continents now separated by huge ocean. Oh, holy cow. Not sure where this period went. Oh no, we still got 3 minutes. Let's get the rest of them. Yeah, we only got 3 more to go. I know we can. Have faith in yourselves, guys. What about rocks matching? Yeah, rocks match. Specifically, what rocks match? Guys, stay with me for the last 3 minutes. Yes, large mountain ranges, now separated by huge oceans. If you put the continents back together, you'll see that they make a perfect line. So over here, the Appalachian Mountains match up perfectly with these Caledonian Mountains over in Britain and Scandinavia. And if we put them back together like a puzzle, you'll see that they make a perfect line, just like the Rockies or the Cascades do today. They make a nice, perfect straight line, meaning the continents had to be together when those mountains formed. So in those sections of the notes, make sure you say something about mountain ranges match across oceans. Now, ice matches. When a huge continent gets covered by a glacier, that glacier will do damage to the rocks below it. These are called glacial striations. We'll learn about them next chapter. But what they found is that the glacier scratched the rocks, and those scratches literally line up again like a puzzle. So when they examined the evidence on South America, Africa, and Antarctica, they have the exact same scratches. The only way they could have got the exact same scratches is if they were once together. So again, evidence is glacial striations on the continents now separated by large oceans. Now this positions don't match one, I think is the one that might have been the most confusing. What did they say they found in Antarctica? Tropical plants. No, they didn't find evidence of ice. They found evidence of tropical plants and animals in the form of coal. Could you grow tropical plants in Antarctica where it is today? No. So how is the only explanation that they had tropical plants and animals then? The continent used to be closer to the equator. Yeah. No, there's no plants in Antarctica at all right now. Nope. So they also found evidence, I think it says in here, that there was evidence of glaciers in places like Africa. Africa's way too hot to have a glacier today. So how could that be? Africa used to be closer to the South Pole. Guys, no homework tonight, but remember you got that quiz coming up on 5 and 10. What you got, Sam? 3? Perfect, thank you. No, yeah, you can do it.
I can do it.
Yeah.